Hello, I'm Dave Casler, amateur radio call sign KE0OG, your guide through the ARRL license manuals. The videos in this course follow the manuals section for section. You can get the ARRL license manuals from the source listed below the video. After you watch the video, dig into the corresponding section of the book, study the associated questions, and then come back for the next video. I'm Dave Casler, amateur radio call sign KE0OG. Hello and welcome to the Amateur Radio Technician Training videos. And with this video, let's take a look at section 2.1 on radio signals and waves. The material I originally put together for this section several years ago still applies nicely, so let's watch that. Afterwards, I have a few additional pointers regarding some additional material in this section. Oh my goodness, right off the bat, they throw all of these weird things to you. The key thing to understand here is the difference between frequency and wavelength. So let's do a few demonstrations. It just turns out that as the frequency goes up, the wavelength goes down. Hams use both frequency and wavelength kind of interchangeably, so it's good to know what they really mean. First, we'll take a look at frequency. That's the easiest one to understand. Frequency is how fast something happens. You know, for example, if you get paid every week, the frequency of your paycheck is once a week. Well, we're not interested in things that happen once a week. We're interested in things that happen millions of times a second. Now, if something goes up and then goes down and comes back to the middle in 1 second, we call that 1 cycle per second, or 1 hertz. That's H-E-R-T-Z, named after a German who did some early work in this area. Now, if something vibrates twice in a second, that's 2 cycles per second, or 2 hertz. Now, audio frequencies, which you're hearing from me right now, start about 300 hertz all the way up to about 15,000 hertz, higher if you can hear really well. And women's voices vibrate a little bit more frequently than men's, and that's what makes them sound higher in pitch. So think of frequency as pitch. In fact, I'll show you on the organ how this is done. Okay, I'm sitting in an organ, and we'll see what happens. The low frequencies down here have a low sound. Now see, as we go up in frequency, there's an interesting relationship between those. A, above middle C, is 440 hertz. C is 256 hertz. If you double that, you come up to C above middle C, and that's at 512 hertz. And it's interesting to note that going like this doubles the frequency, drops the wavelength in half. Now, ham radio operators tend not to work in octaves, this is an octave, but rather in decades or in factors of 10. And you'll see that a lot as you get more into the book. The same thing, of course, is true on a piano. Here's A at 440 hertz, C at 256, and high C at 512, which means this is 1024, 2048, 4096. When looking at frequency, one can think in the same terms as a radio dial. Now, it's real hard to find radio dials anymore. Most things just tune in and you get a little number on it. But I've got a really old radio downstairs that I can show you that actually has a dial on the radio. And the lower numbers are on the left, the higher numbers on the right. And as you turn up the dial, you tune up in frequency. And what we often do is we'll draw a diagram that just has a line, and we'll mark that with frequency just like on a radio dial. And if there's a signal there, we'll kind of mark it in. If there's not, we'll just leave it alone. I'll show you how that works. Now here's this really old radio I was telling you about. It's a Collins 75A4. It was made when I was a boy, and considering the gray hair, you can probably figure out that this is a pretty old radio. Now we're going to take a look at the dial right here, because this is typical of a dial receiver. And as we tune up, we're tuning up in frequency here, 3.9 megahertz, and we go on up here to 4 megahertz or 4,000 kilohertz. This happens to be this line that's from 4 megahertz and goes down to 3.5 megahertz is the 80 meter amateur band. It's on HF. You'll need your general class license to use it, but it's interesting to note that things work exactly the same way down here as they do up at the VHF frequencies that you'll be using as a technician. The wavelength concept comes next. This is a little bit harder simply because it's the inverse the other way around. If you've ever seen a pipe organ in a church, you know that the lowest sounds, which are the lowest in pitch, meaning the fewest vibrations per second, have the longest pipes. And the reason for that is because sound travels at a certain speed, and if you were to sort of draw a line where the peak of the pitch and the bottom of the sound here come this, for a low frequency wave, it's not going to go up and down very many times in the time it takes sound to travel, which means that it will go quite a ways, a long distance, before it starts to repeat. That's a low frequency, long wavelength wave. If you have high pitch, that frequency is vibrating a whole bunch more than the low one, and so in order to get all those vibrations into the same period, we have to have short wavelengths. So short wavelengths for high frequencies. Now, as it turns out, there's a mathematical relationship between them. It's in the book. You can study it. But I want to give you some examples of why this is important in amateur radio, because radios are calibrated in frequency, and we do our antenna measurements in wavelength. And the reason we do that is because it's convenient, and you'll find out why as we go through the course. Basically, frequency is the number that shows up on the dial, and the wavelength is how long you have to make the antenna, because the wavelength has to match the actual electrical wavelength of the wave in free space. Next, I'm going to show you an antenna. This is an antenna that works at 2 meters. 2 meters is one of the bands that you'll be able to use as a technician. As we look at this antenna in detail, we find that the elements of this beam are about the same length. They're approximately a half wavelength at 2 meters, which would be 1 meter or 3 feet. And in fact, that's how long they are. Here's another antenna called a disc cone that is very similar in concept. This is also oriented vertically. This works on 2 meters. It also has an attribute that it can work at higher frequencies too. Okay, now I'm just going to try and illustrate the concept of wavelength. Suppose we're moving at this speed. This is how fast you're moving, and at radio waves, that's the speed of light. And so if you're going along here and you're not oscillating very much, but you're moving forward at the speed of light, you can see that from the start to where it comes up to, again, this is called 1 wavelength. Now, if it turns out that you're doing a lot of vibrating as you move along at that speed, you'll see that the wavelength is much shorter. Okay, so we'll just glance here at what's in there. 2.1, you've got all your different decades here. The ones that are most used by hams are kilo and mega, meaning 1,000 and 1 million. When you get into components, you'll see the tiny little things, but we're not going to worry about that yet. Here they've got some drawings of how this works for frequency, and you get up to the point here where you see how, as we go up in frequency, the waves get shorter and shorter. You can extend this even further, and eventually you'll get to heat and light and cosmic waves and all that sort of thing. They're really all the same thing. Here's an example that I mentioned of how we draw that line across here, put frequency, and if there's something there, we put a line up like that. This is called a spectrum. Look at it. It just means we're looking at it in frequency instead of in time. When you're done, go look at the test questions. Now, let me talk about one thing that a lot of people are kind of curious about. In sound, what's vibrating is the air. You get a pressure wave that's going back and forth at a certain frequency. But what are radio waves? What do they vibrate? The answer is they vibrate something called an electromagnetic field. Is that important for you to know? Not really, except to note that EMF, electromagnetic field, that's why we use E for voltage in all of the things in the book. And it's just where it came from. For many, many years, people thought that there was something called the ether that vibrated, that carried light and carried heat and carried radio waves. It was a real nice fiction, but it turns out not to be so. So just think of them as radio waves in space. The lower frequencies have the longer wavelengths. The higher frequencies have the shorter wavelengths. Let's look now at the concept of units. We use these every day. For example, in the United States, gasoline is sold in units of gallons. Eggs are sold in units of dozens. Milk is sold in units of quarts or gallons. The same is true of radio. We'll get more into this in later lessons, so we'll just take the example of voltage. A simple battery might provide 1.5 volts. A lot of radios run on 12 volts. The voltage in a US wall outlet is about 120 volts, and in many places around the world it's 240 volts. It's stepped down from the street voltage of about 12,000 volts, which in turn is stepped down from huge overhead electrical lines running around 250,000 volts. Well, at this point the numbers are getting cumbersome. So rather than saying 12,000 volts all the time, we can say 12 kilovolts, where kilo stands for a factor of 1,000. Similarly, the large transmission line might be 250 kilovolts. We can abbreviate this as 250 kV. Now, let's go the other way. An antenna receiving a radio signal may receive 0.000000001 volts. Or we could say 1 nanovolt or 1 NV. Now that's the equivalent of 1,000 picovolts or PV. Again, the key concepts here are units. The unit for voltage is the volt. For current, it's the amp, and so on. And the second key concept is the idea of scaling to something manageable by using prefixes like kilo and pico. As the sidebar in the section shows, there are several test questions having to do with scaling. Study them until you understand them. And if you still have questions, leave a comment on YouTube. Lastly, let's look at the concept of phase. Think of the phases of the moon going from full to quarter to new to quarter and back to full again. It's about a 29-day cycle. The idea of phasing in electronics has to do with the relative time difference between a reference wave and some other wave. You'll notice in the text that phase differences are noted in degrees. Well, don't degrees have to do with circles or directions? Well, yes, they do. And there's a connection, but we won't worry about it for quite a while. The key point is there has to be a reference wave and then another wave of the same frequency that is delayed from the reference wave by some number of degrees between 0 and 360. This isn't a new concept. You'll see from the diagram that a wave that is delayed by 180 degrees is always opposite the reference wave. This is where the saying comes from that we are 180 out with someone else, meaning we disagree with everything. Well, that should give you a good start on the material in section 2.1. Thanks for following along with the videos and the book. After you've studied this section in the manual and are satisfied you understand the questions and their answers, come back here for the next video. The ARRL is the National Association for Amateur Radio, and I urge you to join, even if you don't have your license yet. That way you get QST, the League's monthly magazine full of articles for beginners and veterans alike, or you can choose On the Air, a magazine designed specifically for those new to amateur radio. Until we next meet, 73.